All right, so as for your lab number 3, I'm pretty sure you still remember on the schedule, but let me talk about it gradually. Okay, your written test number 1, you can check the dates, but for the guide and examples, I'll try to provide them to you so you know exactly what to expect by the end of the coming Friday. So I'll give you both, the guide, the coverage, and also coverage pretty much fixed, I can tell you right away, and also the example questions. That's what I will do. And so basically, you guys have to study all the lecture materials all the way up to and including today. Okay, so we'll see how far we can go. You can still slow me down. That's okay. So lab 1 and lab 2, you still got to study them. I'll be more precise about what I really expect you to know from lab 1 and lab 2 when you see the guide. But you definitely want to go over the solution again, which I'm pretty sure you have done. And also look more into the in-class discussion about the highlights I made about the lab 1 and lab 2 solution. And there should be maybe a review session for you guys, if that might be helpful, maybe Zoom. I'm thinking about maybe Sunday will be too soon because you guys do need some time to go over material before you got questions. I'm more thinking about Monday, okay? But cannot be Wednesday. That might be too close to your actual test. Let's say 7:30 p.m. on Monday. If you cannot make it, that's okay. It's optional, but I'm going to record a meeting anyway. So I will make it available maybe either on the same evening or maybe the next day, early morning, so you can still get access to it. I'll send you guys a Zoom invite very soon, so you can keep that on your calendar. Take it as a motivation for you to get study, right? Get as many questions as you can. You can ask me during the Zoom. For your lab number 3, accordingly, I would like to delay that for just 1 week. So I'm going to release that next Wednesday. So for now, you can just focus more on preparing for your written test number 1. And as for tomorrow, what's going to work? We still got this 1 hour here for you guys, but I'm going to turn that into office hour. So I'll be in my office from 9 to 10. If you want to ask me anything related to the coverage for your written test number 1, just come by. We can talk, all right? I'll be in my office. You know where my office is. And if you still want to talk to me today, 3 p.m., that's also fine. And also, TA contact information will be the same. Okay. All right, guys, any question, please, about the course? Yeah?
Are you going to hold the office hour tomorrow as well?
Sorry, for tomorrow, yeah. For tomorrow, unfortunately, I got the 2101, another course. I'm the coordinator. I need to just coordinate some items during the office hour, so I cannot be available. Try today, 3 p.m. There might be students asking last-minute questions about 2101, but you can still come. That's not a problem. And also tomorrow, 9 to 10. Yeah, or next week. Next week, regular office hour will just be the same. Okay. Only for this week, a little bit exceptional. All right, if no further questions, let's now move on to a very quick recap, and then we'll continue. We'll see how far we can go today. And as I said, please slow me down if that's too fast. All right, so last time we basically dived a little bit deeper into the grammar, and especially we talk about the 3 different ways to really do to really prove that a particular LTL string potentially is actually a member of the language, right? So you always got to remember about the operator precedence, unary temporal operator, followed by binary temporal operator, and the logical operator, right? So that's something you want to keep in mind. You can look through the example that we discussed last time as well. And then these are the symbols, but I think in the lecture you will mostly see these symbols. But in the literature, you will also see people using these symbols as well. So depending on the paper or depending on the textbook you're reading. But they're commonly accepted. And we talk about basically terminal, like base cases versus non-terminals. And then we talk about how you can actually derive or prove that a string is actually in the language, right? We spoke about 3 different ways. So we spoke about parse tree, right? So just to remind you guys, always remember before you start processing the context-free grammar, you have to consider the operator precedence first before you start drawing the tree or before you kind of start doing derivation so you know where you're going, okay? So you can refer to the detail about the parse tree. There's one more comparison I would like to dive a little bit deeper, which one of you guys actually asked me last time. I want to address that more properly. All right, that's about parse tree, and then you guys got 2 exercises over here. I'll try to give you guys solution a little bit later, but try them out first. Okay. And then we talk about leftmost derivation. That's a second way of showing that the string is in the language. That one there, basically every time you're simply picking the leftmost non-terminal, and then just keep going until you have no non-terminal left. Right? That's leftmost derivation. We did one example in complete details. You can do another 3 as exercises. And also rightmost derivation as well. You just pick the rightmost non-terminal instead, rather than leftmost. All right. And before I move on to some comparison, any question about parse tree, leftmost derivation, or rightmost derivation? Any confusion there? Good? Yep, they should be rather straightforward, right? Okay. And I would like to go to, we talk about basically this comparison here, and then we talk about subformula. I would like to dive in a little bit deeper into these 2 pages today. Okay, let me just start from that. Okay. So Vincent asked me a question during the break last time. It's a very good question here. I want to clarify that and do a little bit more comparison about these 2. Okay, so let's now take a look. So what I want to do is, let's now think about this one here. Okay, we got a parse tree, and we got the leftmost derivation, and also we got a rightmost derivation. Okay, right here. And I want to talk about how we can see the correspondence from the subtree. For example, this subtree here, where can we find the corresponding derivation steps over there. And also, I can talk about another subtree, and let's see where we can find the corresponding steps as well, right? Let's go over that once more. Before I start with that, you can think about the way we usually present the derivation step is by vertical. But to really understand this particular exercise, you may also want to think about horizontal as well, so which I'll show to you. Okay, I'll put it on the top over here. So let's say for leftmost derivation, right? So you can think about, we basically start with the non-terminal right here, right? We'll start with that. So I'm going to say I got the phi over here, and then after derivation step number 1, I have this guy here, which is this implies that, right? And after step number 2, I actually got this. Let me do a few more, and then I'll make my point. So this will be this, and this implies that, all right? And then, yes, let's just do one more. So after step number 3, you can continue for a few more steps. And then once you reach a particular step, you can see that kind of get the subformula you will want to. I'll make that distinction. So in this case, it will be step number 6. I'll explain that. After step number 6, you can see this is what we got, right? So that one there is the future operator P and the global operator Q implies we still got some one non-terminal. So we still have to continue for the rest. Right? So that's like a horizontal interpretation of the derivation steps. So why is this important? Okay, I'll show to you. Let's say I want to consider this particular subtree. Let's say I want to consider this one right here. So this subtree here basically will start with this particular non-terminal, which is the antecedent of the implication, right? You can see this non-terminal here is the antecedent of the implication. So that should be the starting point. So where can we find that? So you can see after step number 1, we got that implication. And then step number 2 is actually going to choose the leftmost non-terminal and then try to derive from there. So that's why we said that you should really start with step number 2 if you want to see the correspondence. All right? So think about for step number 2, what you want to see is, you can see for step number 2, you pick the leftmost non-terminal, and then you want to go from there. And then eventually, after step number 6, you are going to get this particular formula derived. Okay? So this guy over here simply corresponds to the string we have. You can see that one there, we got F, P, and G, also G over here. Right? Let me recap very quickly. The problem is this. We got a parse tree. And then I can pick one subtree over here and ask you, show me the corresponding derivation steps that will correspond to this subtree. The way to see that would be, if you look at the starting point of a particular derivation step, that one there will start by picking the leftmost non-terminal. In this case, it's going to be the antecedents, which is exactly here. So you can see this one here and this one here, they correspond to each other, right? So think about, we got this one over here, And also we got this one over here, right? They kind of corresponding to each other. So that's why we kind of include step number 2, but not step number 1. Step number 1 is actually for you to see the whole implication, not just the antecedents. So that should not be included. So after that, you can see after step number 6, you're actually going to get a whole string over here without any non-terminal. So that's going to correspond to the leaves of this particular subtree, right? So that's why we said to really see the corresponding derivation step for this subtree here, it should be from 2 to 6, right? So that's something I didn't really dive into detail last time, but now you see it. So from 2 to 6 over here, this will be corresponding to this particular subtree. All right. Guys, any question? We're good? Okay, hopefully that's clear. Okay. And then if you see the rightmost derivation, it'll be very similar. What you want to see is here. It will be also, so that'll be 5 to 9 right here. The reason is for derivation step number 5 right here. Is going to pick the rightmost non-terminal. In this case, you can see that from that, what's the rightmost non-terminal? Antecedents. So we pick that, all right? So starting from step number 5, we pick that non-terminal, and then we're going to end up with this one here at the end. So that one is our result. So step number 5 to step number 9 for the rightmost derivation will correspond to this subtree right here, all right? So here we got for leftmost derivation, it will be from 2 to 6. And here it will be from 5 to 9. All right, any question about this? Yeah?
I'm still confused about the starting point. Why don't we start from step 1?
Because you want to think about, okay, think about the starting point for this one here. The starting point is the non-terminal that corresponds to the antecedents of the implication. Agree? Okay, let's agree with that. Step number 2 over here is going to start from picking the non-terminal that's leftmost. However, step number 1 is going to start by picking the leftmost non-terminal, which is here. And that one is corresponding to the root, which is not the subtree root. Better? Okay, good. Very good. All right. Amra. Sorry, I didn't quite catch you. Say that again, please. What? What? Yeah, oh, that's exactly what I would just answer, right? Again, you want to see where the starting point is. If you look at the subtree over here, would you agree the root of this subtree is here, right? The root over here corresponds to the antecedents of the implication. If we started with step number 1, step number 1 corresponds to taking the leftmost non-terminal from here. But that leftmost non-terminal corresponds to the root over here. So it should not be included.
No, I'm asking about the second step in the LMD. The fourth step in RLD. So here we included the second one, but for the LMD, we didn't include the fourth one.
Are you talking about R&D here?
The fourth one in R&D.
The fourth one in R&D? Oh, you mean here? Okay. So this one here, let's see. Yep. Because this one here, yep. Let me see. Think about starting point. This will be picked as the leftmost non-terminal by step number 2. All right? And this one here is going to be picked as the rightmost non-terminal by step number 5. Right? You want to think about which terminal is being picked. So in this case, we are picking this non-terminal, which corresponds to the root over here. And here, we are picking this one here, which corresponds to the root right here. So we are being consistent. All right? All right? Okay, I can see it might be tricky. I can see you guys are thinking. That's good. But do think about how this correspondence happened. Okay, let's do one more example, okay, which Vincent asked me about. Okay, let's say on the same parse tree, okay, how can I identify, let's say, this particular subtree, right here. As you can see, the root of this particular subtree corresponds to basically the consequence of the implication, right? So it's going to be basically for the leftmost derivation is going to be from 7 to 9, but I'll show you how. It's going to be from 7 to 9 over here. It's simply because the starting point for 7 is to pick the leftmost non-terminal right here, which corresponds to the root, the consequence, all right? And then for the rightmost derivation, it's going to be starting from step number 2. Because the step number 2 over here is going to pick the rightmost non-terminal from here, which will be the rightmost, this one here, the consequence. So that's why step number 2 should be included, but not step number 1. Okay? Think about these two correspondences, right? So I think we're being consistent here. So Vincent, that was your question. Does it make sense to you? I want to make sure. It's a good question. I think it's good to clarify. All right. Think about it. You can still follow up with me. Maybe during office hour, I can do some further clarification, maybe in the Zoom review, if you guys want to. All right, so that's about the first thing I want to do. And then let's now do the second thing, about subformulas, which we just started, right? Let's now do it again. So when I was presenting the parse tree in the last few minutes on Monday, I made some mistake, but I just corrected the tree over here. When you see the iPad notes, it's also corrected. But just when you see the recording, it's really the wrong thing, but I'll show to you. So this is really the parse tree that corresponds to this particular formula right here, okay? So we got how many internal nodes do we have? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Basically, each of the 5 is going to be derived into something that contains only terminals eventually. For example, this 5 over here is a non-terminal. It will be derived into some terminals eventually, right? So there's one subformula. So now the question is, we start gradually. The first question is, how many subtrees do we have in the parse tree? We said 10. You just count the internals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? That's what we answered last time. Okay. And the second question. And let me make some space for myself. Okay. We're going to see several questions just to get better understanding about this parse tree. How many subformulas do we have? All right, how many subformula? And notice that I said subformulas. I don't really say subformula without duplication. Okay, sometimes you may have the same subformula in different parts of the tree, actually. In this case, yes. Because you can see somehow I got P over here. I also got P over here. They will be considered as 2 different subformulas. But if I ask about distinct subformula, it should only count once, right? So you gotta watch out how I ask you about it. Okay? So how many subformulas? Basically, every non-terminal phi can eventually be turned into a formula, right? Eventually. So just count the number of phis, which will be corresponding to the number of subtrees. So still 10. And let's now be very precise about which 10 are we talking about, right? Let's talk about it. And I'm going to follow some particular order so it's easier for discussion, okay? So for number 1, let's now do here. Let me start with this particular subformula, number 1. All right? Number 1 here is going to be derived into just P, right? First subformula. And the second one is going to be, let's say this one here. The second one here is going to be derived into R. Okay? And the third one is right here. This phi here. That one there is going to be derived into GR, right? However, I want to suggest some convention here that we're going to follow. In this case, if you simply say GR, there is no confusion because G is just going to be applied to R, right? There's no other operator, so you don't have to worry about precedence. But I would say you can also think about every subformula we're trying to derive, there's some implicit parenthesis around. Just to say, in order for me to apply this G operator, I should really evaluate this subtree first before I can apply G. So every time you have any subformula that's part of it, always put parentheses around. Okay? So what I'm suggesting is, think about there's some implicit parenthesis as follows. Think about there's some parentheses right here, parentheses right here, right here, right here, right here, here, right here. All right? Let's follow that convention. Okay. So what we have is we're just going to have G of R. Okay? Let's go on. Okay? Number 4. Number 4, let me put it here. That one is going to be F, and then we should really got some parentheses, and you can see this subtree here is going to be, number 4 here is going to be, I beg your pardon, it's not F. I just saw that wrong. Number 4 should be right here. So that should be consisting of the implication, right? That should be just the P. Let me just write it down first. That should be the P implies GR. And then the P here is really the 1. And the R here is really 2. And per parenthesis over here corresponding to 2. Okay? We're using parentheses to disambiguate. Okay? One more. Okay, number 5. I'm going to put right here. Okay? That one there is going to be basically just start with F. And then I'm just going to have some parentheses for whatever 4 is going to be derived into. And know that 4 is going to be this one here. I can just copy and paste. Right here. Right? So you can see the correspondence right here. This guy here entirely just corresponds to what F is applied to. Right here. Okay, let's now move on. What about number 6? So for number 6, it's actually going to be right here. All right, so that one there, we're just going to put just Q. And number 7 is going to be right here. Not Q, basically. So we're going to say not Q. Right? You can see 7 here contains the not and also the Q. Right? Almost done. What about number 8? Number 8 is, let's say, this one here. And that one there you can see some duplicates. So number 8 is going to be just P. Okay? You can see 1 and 8 happen to be the same. But since we haven't talked about distinct subformula just yet, so we can still count it. Okay? Number 9. Number 9 is going to be right here. Number 9 is going to be basically about some until operator, which is going to be number 7 until number 8. And we do know number 7 and number 8 already, right? So I can do the following. So number 7 until number 8. And I can just do copy and paste. So number 7 can be copied into right here. Let me just make some space over here. So this is number 7. And this is number 8. There we go. Right? All right, finally. Number 10. Number 10 is going to be the root of the whole tree. Number 10, if you see that, is going to be basically the number 5 and number 9 connected with disjunction, right? That's the final step. So it's just going to be, let's see here, I'm just going to put something here or something over here. And this string here should be from number 5. And this string over here should be from number 9, right? I'll just put them here. So number 5 and number 9. And you can fill it out. Okay? Just a very detailed walkthrough about how we see the subformulas. All right, so we have seen two questions so far about how many subtrees and also how many formulas. So finally, we can ask another question. How many distinct subformulas do we have? How many distinct subformulas? Well, just remove the duplicate, right? You can see number 7 and number 8. They are basically the same subformula, so we don't want to count them twice. So minus 1. So that will be basically just 9. Because number 1 and number 8 are the same. You should only count once. Yeah, I might just give you another example where you might have duplicates of different subformulas, in which case only count 1 for each instance of the duplicates. All right, any question? Go ahead.
When you're enumerating through the subformulas, does it matter like the order you
The order I kind of chose just kind of easier for us to kind of see the process. But when you actually enumerate the subformulas, doesn't matter the order. Doesn't matter.
So you can pick any like order?
You can pick arbitrary order. But I would suggest you try to maybe go a little bit more like a bottom up. Might be a little bit easier for you to gradually build up, right? You may want to start maybe with the shortest one and then all the way to the root, which would be the longest one. Yeah. Also, the way I kind of did the copy and paste, it really shows you how we can reuse the string that's derived earlier from the subtree, right? Good. Alrighty, any question about this? All right, yeah.
How did we get to the number 10?
How did we go to number 10? If you look at number 10 right here, it's basically a tree that's going to be number 5 or number 9.
No, I mean like there's a formula for each tree where we can find the number of subtrees, right?
So are you more talking about the number of subformulas?
Yeah.
The number of subformula just count the number of internal nodes. Yeah. Well, you see the number of 5s that you can see in the tree. Okay. Yeah. All right, any other questions? All righty. Yeah, think about it and then follow up with me if you got doubts. Alrighty, so now we can move on to defining the semantics for the LTL. So far we talk about just syntax. We dive quite deep into the syntax. I think it's a nice insight into the structure of the language. But the next step will be we want to understand how these operations, when they're put together in a mix, what do they really mean? So we're going to gradually build up the semantics or meaning for these operators. As far as your written test is concerned, I'm just going to cover as much as I can today. You guys can slow me down. Maybe just some simple definition about the label transition system. We're going to see some formulation. And I'm going to suggest some background study because there will be some notion about relations, partial function, total function, which you guys learned about in 3342. I already included some resources for you. You can review it. But let's see. It's already on the slides. Let's now go back to the slides. We are done with the syntax, basically. Yeah, question?
Are you going to provide the parse tree in the written test?
So in the written test, I can tell you that most likely you don't really have to submit like your drawing about a parse tree because it's going to be over E-class, multiple choice. So either I'm going to ask maybe some very specific question about the parse tree, in which case you can either choose or maybe you can write some formula. For example, what's the string that's derived from a particular subtree of the parse tree, right? Something like that. Yeah. I'll present the question in a way that you can simply multiple choice. And sometimes you may have to type some short answer.
Okay,
Yeah.
but you are not going to give the tree basically.
Yeah, I think yeah, for written test number 1, I wouldn't really evaluate how you draw the tree as long as you can provide the right answer. Yeah, maybe for the exam will be a little bit more critical about how you draw the tree. So you still have time, to get used to it. Okay. Alrighty, let's now talk about some semantics. Okay. So there's a subformula, and that's also the order I presented. You guys can also take a look. So these are all the formulas, including duplicates. Okay, let's now talk about label transition system, which is not a very new concept, but now we want to get things a bit more formal. So we're going to use what we learned earlier in 3342 to make things formal. So when we define, most likely on next Monday, when we start talking about temporal operator, we will be able to understand what they mean. So we are building up scaffolding for you to understand. Well, let's start with the basics. Okay. So we're going to define what a label transition system is. I'm going to switch to iPad very soon, but it's a formal model. And just remember, whenever we talk about label transition system, there are 3 components you have to define. Okay, we're going to do example today as well. Okay, I'll do also a little bit review about the relation kind of stuff, a little bit, but the detailed review has to be done by you. Okay, let's now talk about these 3 components one by one. Okay, oops. There we go, right here. Okay, and then we also do some exercise at the bottom a little bit later. For now, you can just focus on this definition over here. Okay, so we talk about label transition system, or LTS. And normally, you will just be given some model called M. So think about M is really a formal model. It's a formal model that's actually specified as a label transition system. Specify as a LTS. Okay, and we're going to define exactly what LTS is. We got component number 1, component number 2, and component number 3. And it's not really part of the component, but it's also important to know P, which is what we call a let me just see the name over here. We got S, we got transition relation, and the P. Here. The P here is a set of atoms or proposition that we are concerned about. Okay, so here I'll put it down. Let's start with the P. P is usually not part of the triple we have here. You can see this is triple, 1, 2, and 3. But P will just be given in the context. So P will just be a set of atomic propositions, simple propositions, which evaluates to either true or false. Okay, I'm going to introduce one example, simple example right away. So let's say, for example, the P is a set. Let's say we have one variable called x for our system. It can be 2 propositions, x larger than 0 and also x larger than 4. Right? P is a set of constraints. And normally for each, since we say it's atomic, you don't really have any operator embedded, right? Just simple ones. So you can evaluate each proposition on your states and get true or false. So that's about P. And let's talk about each of the 3. The first one is very straightforward. It's just about a finite set of states. S over here. So this one will be just a finite number of states. Okay, for example, in this example here, I can say I got 3 states. I got state S0, I got state maybe S1, and then I got states S2. Okay, so here I got, for example, x equal to 2, here I got x equals minus 1, here I got x equals 6. Okay, so different states. Of course, in each state, there will be some value for the variable x. And then we also got something called a transition relation. Okay? So this is a transition relation. All right? And as soon as we hit the term relation, there's a big story behind, right? About what a relation is, okay? I'm going to show you guys very quickly about the slides you can refer to after today and before the written test, okay? So if you go to the slides over here, starting from, okay, it's basically say from slide 18 to 28. So these are the stuff that you kind of learn from 33, 42, but you can brush up about the different concept. I didn't really cover all the sets and relation kind of things, everything here, not really. I just chose the relevant one you will need to know in order to understand some example, which I'm going to illustrate later. Right, so from 18 to 28, okay, I'm going to let you study that and reach out to me if you want any explanation, right? Okay, but for today, as we if I can do a little bit review, I'll do that as well. Okay, let me just continue. And relation, the simplest way to understand what a relation is, it is simply a set of pairs. Okay, simply a set of pairs. For example, let's say for this particular stage, this example we're doing over here, you can say maybe there is one transition to go from here to here. And there's another transition to go from here to here, let's say. There might be a self loop. And there might be another transition to go from here to here, right? Now, how do we exemplify this transition relation here? So now I can say the transition relation is simply a set of pairs. What pairs do we have? For example, you're going to put the source and the destination. I got S0, S1. S0, S1. I also got S0, S2. I also have, for example, S1, S1. The self loop. I also have S1, S2. So I got 1, 2, 3, 4, all covered. So we got 4 pairs in the set, right? That's your transition relation. And now you can see right away why it has to be a relation. If you guys recall, what's the difference between a relation and a function, right? Relation simply means a single element in the domain may be mapped to more than one element in the range, right? That's some functional property you can also review. That's on the slides. Let's say for both S0 over here, you can see it either map to S1 or S2, depending on which transition you're talking about. So it must be a relation, okay? Okay, let me put it here. Cannot be a function because a state may be transitioned into more than one states. It's a quick justification about why it should be a relation rather than a function. Okay. Also, because it's a relation, so the more formal notion goes like this. Okay, I'm putting it down here, right here. So we say that this is a transition relation. Okay, symbol here. So this is actually a member of the states relation. So this is something you will see how to understand that when you review the slides. All right. So very briefly speaking, we are basically saying the relation over here tells you the set of all possible relation. All possible relations between S, which is corresponding to the set of states here, and S. And we're saying the transition relation for this particular system is just one possibility. That's why it's a membership operator here. Right? Once you review the slide, this is all explained over there precisely. Okay. All right, so that's about transition relation. And what about the last component? It is something called a labeling function. Okay, I'm going to write it down here. It's called a labeling function. Okay, I'll put it here. And the labeling function formally is defined as follows. L, the labeling function, is a total function. All right? S, total function, and then power set of P. All right, you can see all power set, total function, right? That's all you guys learned earlier, but you just got to review. Okay, it's not that difficult. Okay, but I'm just giving you all the definition right now. One slight confusion you might have, right? Please watch out. This guy over here is a total function. Whereas this guy over here is the symbol for the transition relation in the formal model. Don't get confused. I know they look the same, but they mean something different. Please, okay? So what does that really mean? That means labeling function can be applicable to every state in S. So if I go to S0, S1, or S2, I can simply apply L to it. What I got returned is going to be a set of propositions that are satisfied or evaluated true on that particular state. All right, let's see example right away. Okay. So if I try right here, so the labeling function I'm going to put here. If I say the labeling function I have, if I try to apply that to S0, right? You can see S0 right here. And I got a P over here. I can evaluate both of these. Which one would be true? Larger than 0, agree? Right? If you evaluate x larger than 0, it's going to be true. But if you evaluate x larger than 4, it's false. So only this one here should be returned. That's the atom. That's actually true, right? So this one here is going to give you x larger than 0. So this is the only atom that evaluates to true in that particular state. On the other hand, if I got L of S1, what should I be? Nothing, right? Empty set, which is okay, right? Good. You guys are getting it, all right? So of course, for empty set, you can either say this, or if you say this, equally good. I'll leave that to you. Okay, let's do one more. If I say the labeling function apply to S2, and I'm basically evaluating larger than 4, is actually false. Larger than, beg your pardon. Larger than 0 is definitely true because it's 6. Larger than 4 also true. So both of them, right? It's going to be x larger than 0 and also x larger than 4. All right, there we go. Yeah, so I just kind of showed to you about the formal definition and some example, how you can exemplify. We can do one more, maybe after all these. Right, any question here? Yeah?
Can there be any situation where we would get a set of empty set? Because that's also a part of like power set of P.
You mean like an empty set over here?
A set containing empty set.
Not really. Because if you think about this function here, right? This function is telling you if you're given a state, a member of S, which can be S0, S1, or S2. What's going to be returned is going to be a set of P, right? A power set of P, which means a set of atoms. Here, it can be either just empty, in which case none of them will satisfy, which is exactly this case over here. Or it can be a subset that contains maybe just this, which is this example over here. Or it can be a subset that contains both of them, which will be example right here. So what you say is, if you got just that, no, I don't think so.
Because I was actually confused because that also belongs to like power set of P.
Not really, because if you think about this one here, okay. Let me clarify. Okay, let me say star star. Let's use this example particularly, right? What's the power set for that particular set? It's basically going to be a set of sets, first of all, right? It's going to be either empty, or it's going to be x larger than 0 itself, or it's going to be x larger than 4, or it's going to be x larger than 0, and also x larger than 4. So far, so good? Okay. And by defining this, we're saying that the return value is going to be one of the subsets. So it can be this, which is this. It can be this, which is this. But there is not a member over here that is exactly like that. You don't have it. So that's why it's not there. Mm-hmm. All right? No problem. All right, guys, any other questions? All right, very good. And let's now talk about a little exercise over here. We can see a little bit more formulation. We can put like a universal existential quantification and then try to formulate it. Okay, and for this one, if you don't mind, I'm just going to put it maybe elsewhere, if I may. Okay, you know what, I'll do this. Just make it a little bit more organized, slightly. Okay, right here. So now, based on this particular model definition, now we want to define what's really deadlock freedom. All right, this is an informal description. From any of the states, we want to make sure it is always possible to make some progress. For example, if I'm in this particular state, I'm able to make some progress. I can either go to here, or I can go to over here. If I'm here, I can either go to here or go back to itself. However, if I ever reach over here, I'm deadlocked. I cannot make any further progress, right? That's one example where the system is not deadlock free. But how do we formulate this deadlock freedom condition? By using the components we spoke about so far, right? That's the thing, right? If you got any idea, you don't need to formulate it, just tell me your idea. At least we gotta move a little bit, right? How do we formulate that? You might need to use nested quantification, I can tell you. You might have to. Somehow we want to say for every state, you can make some progress.
And it should be a circular cycle.
Uh-huh.
Like goes to S2
Yeah, of course, you know, I think this is like one particular example, but we want to say for any arbitrary model you're given, how can you formulate like a deadlock freedom condition, right? Mm-hmm. Let me start you with. I can say for every S that is a member of S, right? So the S over here is corresponding to the S over here, right? For every state. And I want to make sure from that particular state, I will be able to make some progress by taking a transition, right? So for example, if I'm in this particular state, I should have at least one way for me to take a transition to move. If I'm here, there should be at least one, yes. But here, I don't have one, right? So now how do we specify this part then? Adrian?
There exists a Z such that Z is in S and the pair SZ is in arrow.
Yeah, that's pretty perfect. Thank you. Yeah. Okay, guys, I'm going to write it down. Your fellow student Adrian just gave us the perfect answer. But I'm going to show you maybe an alternative way to phrase that as well. Okay? Because, okay, let's do that first. So I can say there exists, let's say rather than Z, I'll say S prime, let's say. S prime, that's also a valid state. And then for this part over here, thank you. Absolutely. And for this part over here, I want to say there is a transition possible between S and S prime, right? So visually speaking, I'm basically specifying from S, it is possible to go to S prime by some transition, right? So there are different ways of saying this. And I'm going to enumerate them out to give you a little bit more motivation to really do the background study. All right? There are different ways. I can either say what Adrian said, number one, because a relation is a set of pairs. Approach number one. I can say S prime is a member of that transition relation. Okay, that's approach number one. Approach number two is a relation, so we can use relational image. So I can say, number two, S prime should be the destination, one of the possible destinations after doing a transition from S. Is a member of the transition relation applying the relational image of S. All right, so you got to review the details in the background. All right, relational image. And number three is by using something called domain restriction. All right, you also heard about it. How do I do domain restriction? Basically, I'm saying if I got, okay, let me just make some space for myself over here. Okay, number three. Let's say I got my transition relation right here. Let me start with that. And if I say I want to restrict the domain to just S. For example, if I actually got this particular transition, I'm going to give you one example aside. Let's say, take this one example. If I say over here, that transition relation, I want to domain restrict it to just, let's say, S0. Right? It's going to give me another relation, right? That one there is going to give to me all the pairs that whose first element is actually S0, right? That's domain restriction. That's going to be S0, S0, S1, S0, S2, right? So far you're good. S0, S1, and also S0, S2. Only those, right? And then I want to say somehow the S prime is simply either S1 or S2, right? How do I get S1 and S2? I can get its range, right? And if I say the range of this particular relation is going to be the range of this relation, which is going to be S1 and S2. And I want to say S prime is one of them, okay? So what I will do is I'm going to finish that and you guys can think about. So S prime is a member of the range. The range of this. That's number three. This one has some slight complication, I agree, but it's just a different way of saying the same thing, really. All right, there's another way, at least I can think about, but for that one, they will be very similar to number three. I'm going to put that as an exercise for you guys to think about. Number four, use something called range restriction. And if you're not exactly sure what range restriction is about, look at the background study, right? That's the exercise for you. But the way you define that would be very similar. Okay, quick recap. For this exercise over here, it nicely put nested quantification over here. And then we are basically talking about from one state, it is possible to actually go to another state. So if we can show that for every state in the system, then it's deadlock free. And then this critical property here to say there is a valid transition between S and S prime, you got different ways to specify that. You can either use what Adrian suggested before, transition relation is just a set of pairs. Just say this pair is a member. Or you can use the relational image or you can use the domain restriction, or you can use a range restriction, right? You got 4 possibilities, and you should know all of them. Okay. All right, any question before I move on? All right, good. All right. Very nice. Okay, let me just, why don't we do just one more, and then we'll take a short break. Just one more, please. If you go to the slide, so now we are done with the formal definition here. I'm sure at least you got a big idea. You know what to do for the review. And then I'm going to skip this part, right? From slide number 18 to 28. This is something you guys can review and let me know. Any doubts you might have. Right? I'm going to skip all the way to 29. And then we'll do one more example, and then we'll take a short break. Okay, and then let's now go to, okay, number 29 over here, right? So the way we visualize a transition system is by really a directed graph, but you have seen that already, right? You can see this example here, it is a directed graph, okay? This is a direction. So if you go from here to here, this is the source, that's a destination, right? Directed. And then, so there is one example, we got states, transition, that's good. So this exercise here, you guys can give a try and try to draw the diagram, which is pretty easy. And then from there, you're gonna think about, from that diagram, how do you figure out the triple about the LTS that we spoke about? What should be the S, and what should be the transition relation, what should be the labeling function? It's very similar to the example we just did. I'm also gonna post a solution for you to look at, right? But you gotta make sure you can do it. We can do another example together before we take a break. So this is the example that we're going to use throughout the lecture for LTL. So let's get familiar about this diagram here. But for the previous one, I'll let you do it, and then you can compare with the answer later. Okay, let's now do this one here. All right, so for this one here, why don't you guys try the following, okay? I'm going to start you with something. So so let's assume the following. Always you need to know what's the P, the set of atoms. Let's say we assume the set of atoms P is P, Q, and R. So P can be evaluated to be either true or false in each state. Q can also be evaluated, and etc. So the convention is whenever we put any atoms right beside each state, that tells you that at the state S0, both P and Q evaluate to true. But somehow R is missing. That means R should be false. Okay, let me write it down. So that's just a convention we're going to follow. So the fact that we have this tells you that at states S0, we got P evaluated to true, Q evaluated to true, and R, which is not there, is not true, not R. All right. Similarly, how about this one here? It should be not P, not Q, and R, right? This one really tells you that not P, not Q, R. And for this one over here, this one really is not P and Q and R, right? Okay. So that's the context we have. And what we want to really exemplify is to see how this can instantiate the triple. So the problem is we want to say M, the model is S, the transition relation, and also L. Why don't you guys take a few minutes to see what you can come up with for each of the S, transition relation, and L. All right? Take a few minutes to see what you can come up with. And then we'll go over the answer. Yeah, start in this order so I can gradually tell you the answer. Okay? Adrian.
So, just checking that these labeled transition systems, they do not have any way to put a condition on the arrow.
Yeah, no, for our discussion, we don't. Yeah. Mm-hmm. But what you just describing, it could be some extension, which we don't worry about.
Yeah, like add
You may. Yes, you may. Yeah. Okay, for the first one, it should be obvious, right? Well, it should be S. S0, S1, S2. Easy, right? Okay, I'll let you work on maybe a transition relation. A set of pairs. Okay, that one shouldn't be too difficult, I hope. Good. Okay, let's try the transition relation together. So the transition relation is going to be a set of pairs. So we got S0 can go to either S1 or S2, right? Agree? Either here or here. So S0, S1, and also S0, S2. And what about S1? Can go to either S0 or S2, right? What about S2? You can only go back to itself, right? Okay, I hope I'm not missing anything. Yeah, 5. All right. All right, the last bit will be about a labeling function. All right? I'll be the labeling function. By the way, function itself is also a set of pairs. It's just that the second element in the pair is a set itself. Right? That one there, I'll let you take 1 minute or just a few moments to think about, right? So the L is going to be basically a function which is just a set. Right? It's actually a total function. That means the first element should really cover all the states. It's going to cover S0, it's going to cover S1, it's going to cover S2. But what should be the second element here, right? That's the thing. If you think about the second element, you can go back to the definition for that, definition for that is simply just mapped to a set of atoms, right? Okay. So what should this be? Anyone? Well, it should be a set, right? What would be the set of atoms that can be evaluated true in S0? P and Q. Okay, labeling function here will map a state into the set of atoms that will evaluate to true. That is no-brainer because here we already tell you P and Q, right? Okay, yeah, it's easy. Okay, it's going to be P and Q. For S1, it will be Q and R, and here would just be R. All right. All right. So I think with these examples, I think it's now much clearer about what we're doing here. So these are important because later on, once we introduce you the temporal operators, we're going to use this diagram here to illustrate all the operators, in different contexts. So this understanding this kind of infrastructure we're having is really important. Okay. Okay. Why don't we take a very short break by taking some attendance, and then we'll come back for some little bit more. Okay, so we got about 10 minutes left. So let's just go over a little bit more definition and some example. I think we'll leave the actual semantics part maybe to next Tuesday. So let's see where we can get to. Okay, so the next definition will be about path. Okay, so once you're given some label transition system as a formal model, you want to understand what about path, right? So let's now go over some definition and we'll see the example. What is a path? So you're given some model M, which we spoke about before the break. A path is just an infinite sequence of states. Because we are talking about reactive system, so it's not supposed to be deadlocking. So you should definitely get some infinite sequence as a trace for any execution. All right, let's see some example over here. Okay, and then we'll see more. So one example for the path will be something like this, right? As you can see, let me just make sure. Simple one. I got S0, and then I go to S2. I can go to S2, 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 S2. That's one possible path, right? Already done. And then I will need to clarify some notion here. So one possible path right here is we simply go by this, and then we simply go self loop forever. Okay? Infinite sequence. So we basically got S0 and S2, 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 and so on. Normally, when you're trying to specify some infinite path, as long as you specify enough states and the pattern is kind of clear, you can just say dot, dot, dot. Okay? And let's now clarify this. So the S0, S2, S2 here, they're called the name of the states. S0 here, for example, is the name of the states. And we just happen to start the name from 0, S0, S1, S2. I can also name them maybe A and B and C. Doesn't really matter, right? Depends on the example you're given. However, when we actually give some definition about the different notion about path, and also when we give the definition about different temporal operator, we have to refer to different position in the path, right? And the notion goes like this. So the notion will be, okay, I'll say notions here of path components. This can be another possible source of confusion. The first component in the path will be S1. The second component will be S2. So the index will start with 1, S3, and S4. So we are basically saying for this particular path, the component S1 is the states S0. Component S2 is the state S2. Component 3 is the state S2, and etc. Right? So there's a distinction between the name of the states and also the component of the state. Right? We just got to be careful. So over here we got 1 here, 2 here, 3 here, and 4 here. So these are just indices for the components, right? Okay. And let's now move on with more definition. Okay. And then we'll talk about something called, okay, let's go. Okay, so that's, so that's exactly confusion I will just talk about. Just watch out for that. And whenever we got a path, it's just about a possible future, one possible trace for the model. Okay. And then the next one here will be some exponent notion. Okay, it's not difficult, but I'll just go over with you. You guys know about suffix pretty well from assignment from lab number 2. So suffix really means a path starting from the component Si. Okay, so what do I mean? Okay, I'm gonna show it to you. When you talk about the component here, okay, suffix. So I'm gonna start from here. So we talk about path suffix. Okay, let's talk about this particular, and every time we talk about path, you usually say pi. So you say path pi will be this particular infinite sequence of states. All right, so let's say the following. If I say pi to the power of 0, this is not allowed. The exponent must start with something that's larger than or equal to 1. Okay, first of all, this is undefined. Okay, there's no component 0 because indices start with 1. And if I say I got pi to the power of 1, I'm basically saying give me a path that give me a path that's going to start with component 1, which is just the same path, really. Okay. So you can think about pi 1 over here is just going to be the path starting from component number 1, just like that. Okay. And then this will just be equal to the pi itself. And what about pi to the power of 2? All right. That means I should really start with component number 2. Component number 2 is right here. So start from here. All right. That one there is going to be S2, and then S2, and then dot, dot, dot. Clear? Okay, let's have some challenge here. what about what would that be?
So the one that starts with 2, the one that starts
Mm-hmm. This one here, basically, you can think about, you got to go in order, right? So let's see this one here. You know what? For this one, let me give you a slightly different example so you can easily see. Okay. So for this one here, okay, let me put it here. That's the exercise, but let me give you a different pi. So it is more interesting path. Let's say the pi we're given is, let's say S1, S2, or just say S1, S2, S3, S4. Okay, it's a different pi. Okay, that's the exercise. Okay. Right, so in order to solve this one here, first of all, we have to see what is the path by computing pi to the power of 2. That should be this one here, right? And once we have done that, we're actually going to see what is the suffix of that particular path starting from component number 3. Component number 3, component number 1, number 2, number 3. So that should really start from right here, right? So this one here is just going to be S5 and then etc., which is exactly equal to pi 5. All right? This one kind of shows you how you can manipulate the exponent notation, right? Any question about this exercise here? All right, you guys can think about it. Okay, let me see if there's anything else. Okay, yeah, go ahead.
It's pi to the 2 to the 3. Pi to the 2 is S2 and on, right?
Yes.
But since we're using index 3 and the first index is 1, wouldn't it go from S4 and on, not S5?
Yeah, S4, I agree. I beg your pardon, I made a mistake. Thank you.
It's not addition. It would be addition if you used to set it.
Yes, it's not addition, not really. Yeah, good.
You used to set it one.
Asterisk. Okay, let me correct it and I'll say it again. Thank you. All right, first of all, when we compute pi 2, we're going to start with the second component. And we got this one here. And to the power of 3, component 1, component 2, component 3. So we should start from here, not here. Okay. So it should be exactly starting from here and onwards. All right, very good. Okay, we got 2 minutes, just one more thing. So how do we somehow see the pattern, like for all the possible paths for this particular example here? You know what, I'll leave this maybe unfolding to maybe Monday. It's going to take some time to really explain. So let me just recap about today. So for your written test number 1, you will have to study all the way until slide number 31. Okay, 31, that's a cutoff point, right? And then also make sure you go over lab 1 and lab 2 as well. And then I'm going to send you a Zoom invite about the Q&A. You guys can start collecting questions, but don't forget the background study about sets and relation. You got to make sure you also go over that since we talk about the definition for LTS, right? All right, thank you. And then I'll reach out to you.